part, D.2, prove Fibonacci formula. We do the induction part, mathematical induction part. We verified plenty of base cases. So now we are ready to work on the main part of the mathematical induction. All right, so let's start. So this is, the information we have at this point. Yeah. So when we start, first we need to make our induction assumption. Yeah. All right. Remember, when we applied a mathematical induction on that binary bits problem, I mentioned there are two versions in mathematical induction, weaker version and stronger version. Here, we need to use that stronger version. Yeah, because this problem still a little harder, so than usual, relatively simple problems. Yeah. So we need to use that stronger version. So what's that stronger version? Assume that the formula is true for k between 2 and n inclusive. In this range, that's the stronger version. Okay? In a certain range, so that's the stronger version. Weaker version, we only assume on n. It's true on n. Okay? Yeah. One number. So that's the weaker version. They are equivalent. It looks like the stronger version, we assume a little more, but we can prove, so they are equivalent. Yeah. All right. So now let's apply the, so let's do the main step. The goal, verify when we take the problem size at n plus 1. Yeah. F of n plus 1, not f of, you can say f of, f sub n plus 1. We can use the recursion formula. We can use recursion formula, but at the end we will get this expression. Then we are done. Okay, all right. So that's the main part of the proof work. Yeah. So let's do the formula transformation. To do it, we need to set up. We need to, get our, because we need to work on some specific things, right? Yeah. So we need to get that part. Yeah. Yeah. So let me show you. When we start, we apply the recursion formula. Yeah, for problem size n plus 1. So we have this version. Yeah. After that, we can apply mathematical induction at this point for these two numbers n and minus 1. Because when k equals n and minus 1, they both fall into the range. They both fall into that range. So we can use our induction assumption. Induction assumption on k equals n, we get the first expression. Induction assumption on n equal to n minus 1, we get second expression. All right. Yeah. After that, then manipulate the formula. Try to make it as simple as possible. So we take that 1 over root 5, that constant coefficient, out of the big overall parenthesis. So then all the terms inside that big parenthesis, pair of parentheses. Yeah. All right. After that, here you can see I change the position, I rearrange, I put a phi to the nth and a phi to the n minus 1, those two terms together, and two fractional terms together. Yeah. Two monomial terms together, two fractional terms together. Why I do that? So first, we reorganize our data. Why we reorganize our data? We want to reveal some special structures in our data. Data has structure, right? Yeah. Usually data could have some special structures, but sometimes those structures are hidden. So we need to reveal, after some appropriate manipulation, we can reveal certain hidden structures. Here we are doing that. After rearrange some terms, because it is allowed, right? It is allowed, we can do that. Under mathematical rules, we are allowed to do that. Then special structures are revealed. All right? Yeah. Polynomial part, fractional part. Two parts. Yeah. Then guess and verify. After we examine the structure comparing with our goal. So here, this is the goal. Okay? The goal part. Yeah. Current working part. We do the comparison. Then we can make our guess. Guess on what? Guess on the directions of the proof. When we do the proof, we need to know what directions to go, right? Yeah. So that part we need to make some guess. Yeah. So we apply guess and verify. We guess first, then we do the verification. Yeah. All right. What kind of guess we make? First one, the polynomial part and this also polynomial part, they should be the same because they have the same structure, right? Polynomial structure. Polynomial terms, polynomial structure, they have the same polynomial structure. So we feel the same structure, they should be the same. They should match each other. So we make our reasonable guess, right? Yeah. When you make guess, you have to make good guess, not bad guess. Okay? Yeah. Similarly, the fractional corresponding, the fractional parts should also be the same. That's our guess. The next step, we need to do verification. So to show our guess is correct. Yeah. All right. So the next step, verification. All right. Two parts. Yeah, polynomial part, pretty easy. So then fractional part. Yeah. For the polynomial part, yeah. So polynomial part first. Yeah. When we work on the polynomial part, let us start with our second property of golden ratio. Golden ratio has two properties, right? Yeah. The first property, 1 equals phi squared minus phi. Yeah. The second property, phi squared, this one, second property. Okay. Yeah. So we start with the second property. Okay. Then we multiply both sides, the equality of both sides, phi to the n minus 1th power. After this multiplication, we get our first guess. Exactly the same. Our first guess. right? So it is correct. So we verified the first guess. Second guess. For the second guess, a little more complicated, right? Yeah. Don't worry. This time we apply some commonly used thinking method in problem solving. Yeah. So here we use it. What's that? Backward thinking. Backward thinking. Yeah. Commonly used in problem solving. Very effective. Yeah. Here, let's do that backward thinking. All right. In order to make this correct, right? So we don't know. In order to make that correct, we need some equivalent formula, backward thinking. Move one step backward, not forward, backward. Because we start from our goal, right? Goal should be our last step. Now we start from our last step, goal, moving backward. Yeah, so you know it, backward thinking. Yeah, we remove all the denominators. We multiply a common denominator to remove all the denominators. So we simplify to this new equality. We don't know if it is correct or not. We just need it. Okay? Yeah. We don't know it's correct or not. So we need it. We just need it. All right. Another step backward thinking. In order to make this current equality true, we want to simplify because we want to remove those -1 to a certain number of power. That structure pretty annoying. We want to remove that part. Yeah, annoying. Yeah. So how to remove it? Multiply by -1 to the n-1. That power. Right? After that multiplication, we get 1 equals phi squared minus phi. That is exactly our first property of golden ratio. And we know it is correct. Because this step, we're 100% sure it is correct. So then we can move forward to get to our destination. So now moving forward, yeah. So this step also correct because we have the bottom step correct, right? So then we move forward. Then, because this step correct, we move another way forward. That is correct. Okay. That is just our second guess, right? Our second guess also correct. Then all of our guesses correct. Yeah. So finally, we proved the formula through mathematical induction. And we are done. We're done. Okay? Yeah. Yeah. So here you can see, yeah, this is a good exercise question for us. So give us a chance to practice mathematical induction. Okay? All right, so let me finish our part D.2 right here.